2 minutes. Maybe we should wait 2 more minutes.
Okay.
28.
Hey, Mark, how are you?
Hi, good. What about you?
I'm good, actually. So I actually told Michelle you would be in office, actually. So
Yeah, no, well, I think it's just simplest to stay home these next 2 days.
yeah, because after this talk, I think Michelle is gonna organize a King's College tour with those colleagues, actually. So.
Yeah, I had some email contact with them about that. But I also, there was a COVID case at the conference last week, so I think it's best for me to wait till I'm clearly clear before I.
Okay.
So
Okay, almost time.
Hey, Mark.
Hey,
Phil.
I'm not sure who just said it.
Nice to see you again. I don't know. Oh yeah, you can see my arm.
Okay, I'm gonna say that it's time. Let's start.
Okay.
Okay, he's gonna start recording. 1 second. Okay, so I understand. Okay, so it's a pleasure to have Mark Ross. He's gonna tell us about mirror symmetry. Thank you very much.
Okay, well, thank you very much. So I mean, it's a bit strange giving the very first talk of the school. I'm going to give a historical introduction to mirror symmetry with an aim to get to explain some of the issues that we're going to be seeing, hopefully seeing this week. I think the subject can be a bit overwhelming for young people just getting into the field because there's so much work being done, so many different directions. The field has grown up over 30 years. And so I always feel it's helpful to give a historical introduction to the field. Those of us who are unfortunately old enough to have been around from the beginning obviously saw history in action, but it's harder for young people.
So, Mark, the bigger you write, the better.
Okay, is this visible?
It's borderline. So don't write slow.
Okay. Yeah, so let's start with roughly 1989, which is when the subject got started. And it was really work of Green and Plesser, Brian Green and Brian Plesser, constructive mirror to quintic threefold. Now, let me be explicit so we have some example in mind. Let's take x psi to be the zero set of the equation x0 to the fifth plus ... plus x4 to the fifth plus, let me know if this is readable. I hope this is bigger.
It's readable, it's good.
Okay. So we take this equation, so Fermat quintic plus psi times the product of variables. Think of psi as a parameter in the complex plane, and this is a hypersurface in CP4, a quintic hypersurface. So the general member of this family has Hodge diamonds. So if you write down the Hodge numbers, H00 is always 1. There's no, the first Betty number is 0. So H10 and H01 are 0. The second Betty number is 1, and all those in H11. The third homology is pretty big. It's 204-dimensional and splits up under the Hodge decomposition into space of these dimensions. And then, of course, it's symmetric. So we have, sorry, it's gotten a bit smaller at the top. But hopefully, so the key point is H11 of x psi, or general psi, is 1, and H12 of x psi is 101 dimension. Okay, so that's the basics about a quintic threefold. Now, what they did was they constructed the mirror as a resolution of a quotient of xi. So we consider the following group. So consider G contained in Z5 to the fifth mod Z5. So here Z5 is given by the diagonal embedding Z5 to the fifth. That's A goes to A, and G is the subgroup consisting of tuples A0 through A4, such that the summation of AI is equal to 0. Of course, mod this diagonal Z5. Now, how does G act on Xi? Well, it acts on P4. By a tuple A0 through A4 takes a point with coordinates X0 through X4 to a point with coordinates C to the A0, X0, to C to the A4, X4, where C is a primitive fifth root, we say each of the two binomials. Okay, so this gives us an action on CP4. We divide out by this diagonal subgroup because that acts trivially on CP4 since it just rescales the coordinates. Okay, so and in particular, the equation that I wrote down, if we go back to this equation, you can see if we rescale each coordinate by some fifth root of unity, this part is left invariant. This term is left invariant by elements of G because of this condition, the sum of the AI should be 0. So this equation is invariant under G. Xi is invariant under G, so we get a G action on Xi. So we get a quotient Xi mod G. Now, the initial problem was that this was extremely singular. And if you want to get something useful like Hodge numbers, what we should do is resolve the singularities. And we can show there exists what's called a Crepin resolution, which I'll write as X check psi, Xi mod G, i.e., the canonical bundle of this Crepin resolution is the trivial bundle. That's what Crepin means, at least in this context. Okay, so this is again an example of what we call a Calabi-Yau. Maybe I should have said that omega x psi is already trivial. That's an easy exercise from the junction. And this is called the Calabi-Yau condition. The variety is Calabi-Yau if the canonical class is the canonical bundle is trivial. So the sheaf of top dimensional, top rank forms, holomorphic or algebraic forms.
So the resolution you're talking about is using G-Hip scheme, or?
It is using, sorry, I didn't catch that.
I mean, so they are using the work of Bridgeland, King, and Reed.
Oh, no. This is much simpler. It's just an algebraic geometric resolution of, and this was carried out, I believe it was carried out in work by Rowan back in, who was working with Green, maybe Green and Rowan. It's essentially a toric resolution.
Oh, I see. Thank you.
There's nothing sophisticated in it.
Oh, okay.
Well, in 1989, it was sophisticated, but okay. So the Hodge diamond of X check psi is, again, this was computed in work of Rohan and possibly Green, is now 1, 0, 0, 0, 101, 0, 1, 1, 1, 1, 0, 101, 0, 0, 0, 1. So the crucial point here is that we've really interchanged Hodge numbers. So crucially here, x11 of x psi equal to h12 of x hat psi, x check psi, h12 of x psi equal to h11 of x hat psi. And this represents a symmetry about in the Hodge diamond about this axis. So if you reflect around this axis, you get the you get the other Hodge diamond. And this is, as far as I understand, the reason why the word mirror symmetry was introduced. There wasn't anything really deeper about that than this reflection about this diagonal axis. So sometimes I would call this is sort of a topological test. Of mirror symmetry. If you think that you constructed a mirror to something, this is the kind of the first thing you should check. Okay, so the crucial thing here that got the subject started was work of Candelas, Looijenga, Green. Notice this is a different Green because there's no E on the end. Green Parks. And what they did was they followed sort of string theory, followed implications of string theory, and they calculated what we call period integrals of the form. So integral of alpha over some cycle alpha of omega psi on x hat psi, where alpha is some 3 cycle on x hat psi, the integral, and omega psi is a family parameterized by psi of holomorphic treeforms. So the fact that the canonical bundle is trivial means that you have nowhere vanishing holomorphic treeforms. So you need to choose for each psi, you choose such a holomorphic treeform, and you calculate these integrals. Now, that's not so easy to do, and what you do with these integrals is then somewhat complicated. But they had a number of miraculous guesses that turned out to be correct. And at the end of the day, what they get from this is a generating function for the numbers N, D. And very roughly, this is the number of rational curves of degree D contained in x psi in the original quintic threefold. Okay, so I've left out a huge amount here. Let me just give some indication about what these numbers are. So N1 is the number of lines. This was known to be 2,875 on the general quintic. N2, that's the number of conics contained in the general quintic. 609,250. This was due to Shelton Katz. in 1986, and N3 was 317,206,375, was due to Arnold and Strummer. Again, so essentially simultaneously with this work of Cadell, Stoss, and Green and Parks. Now, there's a huge amount of story I'm leaving out here. First is making precise what these numbers mean. Of course, I'm not telling you also what this error really is. There's some long, complicated procedure, but it is something you can carry out. And these days, the numbers ND are called Gromov-Witten invariants. So this is one of the basic concepts of modern enumerative geometry. So Gromov-Witten invariants are curve counting invariants. I'm not sure to what extent, I mean, we will certainly see as the next 2 weeks go on, lots of examples of Gromov-Witten invariants. At the time when even Allinger and Strummer did their work, there wasn't a notion of these invariants, but they developed over the next 5 years so that one can make precise and rigorous what these numbers ND were, and then have the hope of actually showing that the Cadell et al. Calculation actually gave the right answer. So of course, everything they did was justified by rather non-rigorous physics. The fact that they got these first 3 numbers right was already a miracle. I think the first number, 2875, is kind of comes out from normalization procedure. But you're not going to get the next 2 numbers by accident. So this essentially gave a conjecture for mathematicians to prove that the generating function they produced really was a generating function of the number. And this was first proved by Guggenthal and later by Yu and Yao, gave a slightly simpler thing, and then many other people. This starts in 96. They gave proof that the physics prediction for the numbers ND are correct. Now, perhaps that 1996 started the real period of rigorous mathematics. But before that, there were a number of rigorous mathematics of mirror symmetry. But before that, there were a number of works of bridging the physics and the mathematics literature, trying to sharpen our understanding as to what mirror symmetry is about. I always like to say that mirror symmetry it was something given to mathematicians by physicists, which you can think of as like a bit of 21st century mathematics that fell into our hands. It'd be sort of as if an iPad was suddenly given to a 1950s era computer engineer, and they have to figure out how it works. So the fact that this kind of calculation actually works is amazing and needs to be explained. Now, let me sort of mention one key point, which will come up as we go on, a key point that was understood in the early 90s, is that a mirror is associated not to a given Claudiel, but rather to what was originally called the large complex structure limit, degeneration of Claudiels. So this was terminology that came from physics. I think now in mathematics we view this as slightly more general. So what would we think about? So let's consider a degenerating family. So here D is a disk, and this is a flat family of Calabi-Yau varieties. And here, so xt, they should be non-singular, so it'd be smooth Calabi-Yau for t not equal to 0, but x0 might be quite singular. And we have the puncture disk sitting here, and then the family of smooth Calabi-Yau sitting over this. And we can then look at the monodromy action coming from this family of the puncture disk. What does that mean? Well, let me draw the puncture disk. Here's the disk here. And let's take a little loop based at some point, say T0. Take a loop around here. Over this, we have some Calabi-Yau. I'll draw that. And we can consider cycles. Let's take maybe a little, it's a very badly drawn cycle. Let's take a little loop here. In this example, it's an elliptic curve. The cycle is a circle. And you can follow the cycle around the loop. You can parallel transport the cycle. And when you get back, you might find you come to a different cycle. And this gives what's known as a monodromy transformation. So if we call the loop gamma, we get a monodromy transformation T gamma. So this goes from, say, the homology of xt0 to itself. This is given by parallel transport of cycles. Around gamma. Now, it follows from general Hodge theory there's some numbers a and b such that t gamma minus the identity, the power b equals 0 for some integers a and b. Now, this is called quasi-unipotent monodromy. T gamma is quasi-unipotent. Now, the large complex structure limit is now what we call, usually just referred as maximum unipotent. I.e., first of all, being unipotent means we can take A to be 1. And the power we need to take to kill off T gamma minus I is n plus 1. So T gamma minus I is the n plus 1 is 0. T gamma minus I to the n is non-zero. And this is where n is the dimension of phi, a dimension of the Calabi-Yau. Okay, so this monodromy is, another way of putting this is saying that this has a Jordan block of size n. But you should view it as really saying that the central phi graph 0 is particularly degenerate. And in particular, if it's normal crossings, just a union of varieties meeting transversely, then X0 has a zero-dimensional stratum. In other words, there is some intersection of n divisors inside X0, which is non-empty, so n irreducible components of X0, giving you a zero-dimensional stratum. Okay, so a typical example is one we've already seen, e.g. for x psi, when psi goes to infinity, we get the central fiber given by X0 product of the variables being 0. So that's a union of 5 P3s. And if you intersect 4, then you get a zero-dimensional. You get a point. Okay, so this is something I want to emphasize. I think we'll see this throughout the next 2 weeks, that somehow you really need to have some quite degenerate something around in order to expect to get a mirror. Okay, so that represents the early 90s. There are a couple of developments that any historical survey needs to touch on. The first is Batro's construction. I'm going to say very little about this. But he gave what is still really the gold standard as hypersurfaces in toric varieties. So this is 93. The paper came out very soon after this came to mathematicians' attention. Okay, as I said, I'm not going to say anything more about that. In 1994, Kontsevich made the first sort of, well, somewhat rigorous mathematical approach to explaining mirror symmetry. This is with the homological mirror symmetry conjecture. Now, this has become one of the main threads of mirror symmetry research, and I think we're going to see a lot of it in the next 2 weeks. Now, very roughly, what he said is that if you have a mirror pair, then, so the philosophy is that the complex geometry of X should be isomorphic to the symplectic geometry of check X. And he made that precise in terms of categories. So there's something I'll say a few words about what these things are. But again, I hope we see more of these over the course of the next 2 weeks. So this thing on the left is the bounded derived category. So I can't spell today. It's the bounded derived category of coherent sheaves on X. So roughly what you do is you take the category of chain complexes of coherent sheaves on X, bounded chain complexes, and then there's a standard process for getting a so-called derived category out of that localizing quasi-isomorphisms. This, on the other hand, is something called the Fukai category. And this is a category, well, first of all, it's not a category, so let's not worry about that. But the objects are Lagrangian submanifolds. Of X check, and the morphisms are Floer chain complexes. Now, let me say a few words because I want to define Lagrangian if you haven't seen it. So first of all, we should think of X check as carrying some choice of Kähler. In theory, it should be determined by the choice of complex structure on X. Complex structure on X should reflect symplectic structure on X check, and the Kähler form omega check is a symplectic form. And L contained in X check is Lagrangian if, first of all, the dimension of L is, as a real submanifold, is equal to the complex dimension of X check as a complex manifold, and omega check restricted to L is 0. Okay, so those are some fundamental objects in symplectic geometry. The Floer chain complex are complexes generated by intersection points of Lagrangians. Again, I don't want to say anything more than that.
Mark, can I say something to the people here before we go? So this is very fast, probably, for all, but you can kind of keep track of the questions, and then we can discuss after the talks end. Okay. So take notes of the things that were particularly confusing or what you didn't understand and so on. Okay.
Yeah, I guess I'm at
I mean, it's just we will try our best to fill in the gaps here.
Right, yeah. So I think I wouldn't expect that any sort of beginning graduate student to understand exactly what I've said, but rather I want you to go away with sort of an overview. These are the things that one needs to understand more deeply.
Yeah.
So obviously, this is extremely cursory summary of homological symmetry conjecture, and one could teach a whole course just trying to define these gadgets. And in particular, when Kontsevich made his conjecture, this was not a particularly well-defined gadget. And the difficulties involved are very complicated. One of the very first issues is that this is not a category. Composition of morphisms is not associative. And this is what's known, in fact, as a infinity category, which I'm not going to define in this talk. So part of the work even involves trying to make sense of what it means to say that a category, a genuine category, is isomorphic to something that's not a genuine category. And so, getting the foundations of Floer theory to define morphisms, that's another enormous project. So it was a long time before one could really say that this conjecture was, everything in this statement was well defined. Okay, so that was the first attempt to understand the geometry underlying mirror symmetry. The second attempt.
So there's a question, I think.
Yeah.
So if you find the next check that satisfies this homological mirror symmetry conjecture, does it satisfy the topological test as well?
So in dimensions, one has to have some caveats. It's not, I don't think it's automatic in all dimensions. What you do know is that the Hochschild homology of these two categories are equal because the categories are isomorphic. And the Hochschild homology of the banded derived category involves some sum of Hodge groups. And so, again, you have to use some additional information. Dimension 3, I think, is true, but may not be true in the higher dimension. I don't know if we know any counterexamples.
Thank you.
Yeah, so if a pair of Clavius satisfies this isomorphism, it would satisfy the homological test of mirror symmetry. If you can compute genus zero Lagrangian variance, it would satisfy the normative test. Okay, so the other major 1990s point of view on their symmetry is the so-called Astronomer-Alsace conjecture. And so this was 1996. And again, this says if you have a mirror pair, then there exists what we call special, dual special Lagrangian torus vibrations x to b, b is some other gadget, and x check to b. Now, what does special Lagrangian mean? So here L contained in X is special Lagrangian, or just like say special, if the imaginary part of, say, e to the I theta times omega restricted to L is equal to 0, for omega, a homomorphic N form, non-vanishing, nowhere vanishing, say not equal to 0, and theta some angle. Okay, so we already know, I already told you what Lagrangian meant. So special is an additional condition having to do with the complex structure. Because you think of the homomorphic N form as determining, in fact, it does determine the complex structure on X. Okay, so putting this together, so what does this mean? It means that we have two maps. We have a map from X to B, and we have a map from X check to B, whose general fibers are tori. So general fibers as well as F check, general fibers of F check are special Lagrangian tori. And I use the word fibration here to indicate that possibly not all fibers are tori. Otherwise, I would say torus bundle. And the reason you have to allow some fibers that aren't tori is otherwise you're not going to get particularly interesting topology. Now, this conjecture has in some sense made much less progress than the homological mirror symmetry conjecture. Maybe I should say something about the word dual here. So dual tori is if we have a vector space V model, a lattice lambda, and lambda can be a lattice, then the dual torus can be thought of as the dual vector space modulo the dual lattice. So there's a well-defined notion of dualizing a torus. The conjecture as stated left open many, many different questions. How do you do this dualizing more globally? How do you construct special Lagrangian fibrations, and so on and so forth? And anyway, what does this have to do with earlier forms of mirror symmetry? So this strong form, there's been no progress in the strong form for general quadrats. And it's probably not true in the strong form. And let me just mention the best results to date are by Yang Li. I think this is a couple of years old now, maybe 2019, I might be wrong, where he constructed special Lagrangian vibrations on open sets of a quintic threefold. And these open sets get bigger as you approach a large complex structural limit. So special Lagrangian vibrations on open subsets of quintic increasing in size, filling up more and more of the quintic as we approach large complex structural limit. Okay, so the main point of this is that the strong version is just very hard. It's hard geometric analysis, even constructing examples of special Lagrangians is very hard. Now, fortunately, there's a lot we can learn from the conjecture without solving this hard, strong formula. And I'm going to get slightly more detailed. So here's a toy version, which is very informative. So let's let B be an integral affine manifold. Now, what is this? So this is a manifold B with an atlas, say a bunch of open sets UI of B and charts UI and Rn, such that the transition maps so psi I composed with psi j inverse are affine linear with integral let's say y goes to ay plus b, where A is a integral invertible matrix, A is in GLNZ, and B is in Rn. Or sometimes I might want to consider Z. Okay, so this is a fairly sort of combinatorially rigid kind of gadget. We're gluing together charts using affine linear transformations. Now, if you have one of these, we have two lattices. Or is lambda contained TB. So this is a family of lattices inside the tangent bundle, or a local system, if you will, contained inside the tangent bundle. With lambda locally generated, by d dy1 through d dyn, where y1 through yn are affine coordinates, or coordinates in one of these charts. If you change these coordinates by an integral affine linear transformation, of course, these fundamental vector fields will change, but the lattice they generate doesn't change. And that's why you need A to be in GLNZ. But this is generated as a group for lattice. Okay, we also have a dual local system, lambda check contained in the cotangent bundle, locally generated by the corresponding differentials dy1 through dyn. And again, under affine linear change of coordinates, that lattice is well defined. Okay, so what do we do with this? Now we define x of b is the tangent bundle of b modulo lambda. So we divide out each tangent space by the corresponding lattice. And this maps down to b. This is a Tn bundle. And x check of b is similarly defined as the dual gadget. And this also maps down to b. So these are two Tn bundles which are dual to each other in precisely the sense I defined earlier. Each fiber on the left is the form b mod lambda, and on the right is the form b check mod lambda, b dual mod lambda dual. Now, these things come along with a little bit of more structure. So x of b carries a canonical complex structure. With I don't want to write down the full equation, but with the j, the almost complex structure operator, interchanging horizontal and vertical tangent spaces. Okay, so you have the tangent spaces to the torus fibers. Those are, by construction, isomorphic to the tangent space to B. And we also have a fact connection on TB given by the local system lambda, so we have horizontal tangent spaces. Those are canonically isomorphic and interchanged by J with a minus sign to get J squared being minus the tangent. So the other one, x check of B, carries a canonical symplectic structure. Inherited from the canonical symplectic structure on the cotangent bundle of B. The cotangent bundle of any manifold carries this canonical symplectic form, and it's easy to check that that descends once you divide out by lambda check. Okay, so the picture is now basically half of the SYZ conjecture with x of B down to B. This is special torus vibration, and x check of B down to B is a Lagrangian torus vibration. And now, having forgotten half the structure on each side, life becomes quite a bit easier. Okay, so nevertheless, this is still very much a toy situation because these are torus bundles. I should have probably written bundles here. And to make this interesting, well, okay, so this gives a very satisfactory picture. Of mirror symmetry for abelian varieties, which are examples of Homophobia. But past that, you're going to not get very far. So what you have to do is allow singular fibers. You have to allow these tori to degenerate. And to do that, what we'll do is we'll allow there to be points of B where the affine structure doesn't extend. So let me define an integral affine manifold with singularities is a manifold. I'm going to put maybe, let me put a question mark under this, because in general, it can be slightly weaker than manifold. B with an open subset, B0 contained in B, carrying an integral affine structure with delta, which is a complement of B0, of codimension 2. So there are a lot of examples of these. And so, for example, in dimension 2, obviously in dimension 1, there's nothing interesting there. They have to be, no delta has to be empty. But in dimension 2, it is possible to construct examples of 2 spheres with 24 singular points. So 24 points of delta, so number of points of delta is 24. And such that the monodromy of the torus-fied bundle that you construct, or this can also be detected inside the affine structure, is the form 1, 1, 0, 1. So that's the monodromy. Think of the torus bundle, or think of lambda, monodromy in lambda. That's the best way to say this. Maybe I'll make this a bit bigger because it's important. Is 1, 1, 0, 1, or conjugate to 1, 1, 0, 1. Okay, so it's not too hard to construct such examples. They're essentially sort of combinatorial in nature. Okay, so now comes our problem. We have this lovely corresponds to an x of b and x check of b, which will be this very toy version of mirror symmetry. But now we have only x of b0 sitting over b0 and x check of b0 sitting over b0. Now, somehow we want to extend these vibrations to b. And what we would like is something like a picture like that and a picture like that. So in general, if you just gave me an arbitrary integral affine manifold with singularities, I would probably have no idea how to do this compactification. But we do know, for example, in dimension 3, or less than or equal to 3, with a restricted class of singularities, this is, the word is simple. I'm certainly not going to define. Sorry, there should not be a 0 there. That's the whole point. The red diagram on the right exists in a symplectic category. So in other words, there's a way, at least in nice cases, of compactifying this symplectic manifold to a compact symplectic manifold or something across the singular points. And this is due to Castagna, Barnard, and Matthesen. Now, there's some moral in this, which is that somehow the symplectic structure that I told you about on X check of B0 is really the correct one. And that really comes from what's known as the Arnold-Louisville theorem. The sort of symplectic structure. On X check of B0 is unique, at least locally, by something called the Arnold-Louisville theorem. There is only one choice of complex structure, sort of symplectic structure, which gives you locally a Lagrangian torus vibration, compatible with the given Mathematical structure in some sense. However, so that's good. Symplectic compactifications are good. The problem is that on this side, you want a complex compactification. This was a complex manifold, and you want to compactify as a complex manifold. And that, in general, fails. And here, the moral is that actually the complex structure I told you exists on X of B0 isn't the only complex structure around. You could start to deform it away from the kind of nice, simple complex structure. So on the right, on the left, in general, there does not exist. There does not exist a complex compactification. And corrections to the complex structure are necessary before compactifying. Okay, so somehow you need to deform, you need to perturb the complex structure, and you need to do that in some intelligent way so that you have any hope of actually extending the complex structure to the compactification. And in a sense, that's really what people have been trying to do in sort of the SYZ approach to mirror symmetry for the last 20 years. So to be useful, this perturbation, or these corrections, could have something to do with J-hole curves, or in fact disks on X check of B. So I think that's kind of where I want to end. There's going to be a lot of, certainly going to be any number of talks explaining how this works. In particular, Baron Siebert and I will elaborate on our approach to this problem next week during the conference part of the 2 weeks. But we will see various tools. I think we should learn about things called scattering diagrams, which are data structures for encoding how you perturb the complex structure. So this at least gives us an introduction to some of the fundamental gadgets that will be showing up. Not all the gadgets showing up over the next 2 weeks, but some of the gadgets showing up. So perhaps I'll end.
Okay. So thank you very much. Let's thank the speakers.
Yeah.
Okay, so any questions? First from here. maybe. I think there are many questions.
Okay.
What about the example of sphere with 24 points? Into none for the complex the left hand side.
Sorry, I couldn't make that out. I wonder.
The question is, what about the example with 24 singular points on the sphere? Is anything known about the complex picture? If you start
yeah,
with
so
the complex side.
yeah, so we have algorithms for producing the mirror, so I can start with that gadget with 24 singularities, and we can produce the compact fly, the X of B, but only in a certain formal sense. So what we tend to do is, so in fact, we never, I mean, maybe in some simple cases one can, and this Janita Wu, for example, worked out some simple cases where you can explicitly describe this as a complex manifold. But what we actually do these days is that we construct X of B instead of constructing X of B, we construct formal families. The simplest would be maybe write as X completed over spec K double bracket T, where you should think of the generic fiber as being the compactification we're looking for, this X of B. Now, of course, this means we're working in a quite different context than I introduced, but the problem is that you very rapidly run into convergence issues in trying, if you start with a sphere of 24 singularities, you get overwhelmed by all the corrections, and trying to show convergence to show you really have actual compact complex manifold is very difficult. But this fits with the philosophy I mentioned earlier. This really is saying that we can understand things very close, in this case, formally close to the large complex structure limit point. You should think of this sketch as really being degeneration, a large complex structure limit degeneration. I don't know if that helps.
So can I continue with this? Like, what's your opinion about the future of the complex version of how do you see it? Do you expect that if we do more work, then we will be able to show that this formal family really gives rise to an actual complex family, or do you think we should kind of maybe give that up?
So I'm not sure if I would have much hope for being able to prove convergence. Let me say, I would be pretty surprised if convergence could be proved for the general construction. With that said, I think there's still a lot of value in sort of relating the older point of view to this point of view. And let me mention particular work of, I believe it's Conan Lung, Kwok Chan, and Ma, but I might have the set of authors slightly wrong, where they went back. So if I had a bit more time, I would have talked about Fukaya's first suggestion along these lines in 2001, where he was really the first one to attempt to understand this compactification. And he gave some intuitive argument that the equation governing the deformations of complex structures, the Marov-Cartan equation, gave some intuitive argument that after doing some kind of Fourier expansion, you should get solutions that are concentrated along tropical curves, and that really brought the tropical geometry into the picture. Again, I haven't mentioned much about that. But there's this lovely work of Lung et al. Actually then goes backwards, says, well, now we understand these scattering diagrams. Now let's go back and understand the asymptotic analysis and actually try to make it rigorous. And they've done quite a lot in that direction, but it is still essentially formal.
More questions? Maybe online questions, if there are any? Okay, well, thank you very much for the beautiful talk. Let's thank Mark Russell.
Okay, thank you.
Okay, well, see you next week.
Yep. Okay.
Have a good day.
All right.